Deep in our galaxy lies a black hole so powerful it can outshine the stars around it. V404 Cygni. What makes this one so wildly active, bursting with energy and light? Tonight we'll uncover the secrets behind its cosmic storms. If you enjoy the mysteries of space, please like, subscribe and share, and tell us in the comments, do you think black holes create or destroy more than we imagine? Thank you for watching. Now let's begin. V404 Cygni is an extraordinary and active black hole located in the Milky Way galaxy, approximately 7,800 light-years from Earth. Discovered in 1989, it immediately intrigued astronomers due to its distinctive properties. The system itself is situated in the constellation Cygnus, and is part of a binary system in which a black hole and a companion star orbit around a shared centre of mass. This specific system has become one of the most studied in astrophysics because of the extreme behaviour exhibited by the black hole. The black hole itself is relatively small compared to some of the supermassive black holes found in other galaxies. However, what it lacks in size it more than compensates for in activity. This black hole stands out not only because of its active nature, but also due to its position in the Milky Way relatively close to Earth compared to other black holes. Its proximity has made it a prime candidate for observation, providing astronomers with valuable insights into black hole dynamics. It belongs to a category known as stellar mass black holes, which are typically the remnants of massive stars that have undergone gravitational collapse. The most intriguing aspect of this black hole, however, is its level of activity. While many black holes remain dormant or show very little variation in their emissions, this particular object exhibits significant variability in brightness and energy release, making it a unique object of study. The black hole is capable of emitting powerful bursts of energy, particularly in the form of X-rays, which has led scientists to explore the mechanisms behind these extreme emissions. These bursts are among the brightest X-ray sources in the sky, and have been observed to increase and decrease in intensity on timescales of just hours or days, which is unusually fast for a black hole. This behaviour has made it one of the most important objects in our study of active black holes. The binary nature of the system further complicates our understanding. The black hole is locked in orbit with a companion star, which is an important factor in the behaviour of the system. The star, while much larger than the black hole, is steadily losing material to the black hole due to its intense gravitational pull. This process, known as accretion, forms an accretion disk around the black hole, where material spirals inward, becoming increasingly heated and emitting vast amounts of energy. The material in this accretion disk is torn apart by the black hole's gravitational forces, creating intense radiation across multiple wavelengths, including X-rays, gamma rays, and infrared. These emissions are not constant but fluctuate dramatically, producing X-ray bursts that can temporarily outshine entire galaxies. The outbursts are so powerful that they can even affect the space surrounding the black hole, influencing the nearby interstellar medium. The behaviour of this black hole is an exceptional example of how such objects interact with their environment. As the material from the companion star falls into the black hole, it forms a hot glowing accretion disk, which is responsible for much of the radiation emitted by the system. These outbursts are not only scientifically interesting, but also provide a valuable opportunity to study the inner workings of black holes. As the black hole consumes matter, the intense heat and radiation produced can be observed across vast distances, giving scientists a unique window into the forces at play around such a powerful gravitational object. In recent years, advanced technologies have allowed astronomers to monitor this active black hole in unprecedented detail. Instruments such as the Chandra X-ray Observatory and the Swift satellite have been key in tracking the behavior of this object. The ability to measure and analyze the X-ray bursts has provided insight into the nature of the accretion disk and the role it plays in the black hole's emissions. Through these observations, scientists have been able to create detailed models of the system, helping to improve our understanding of how black holes behave in binary systems and how they influence the surrounding space. The rapid variability of the X-ray emissions has led to significant breakthroughs in the study of black hole physics. It has also raised questions about the mechanics of accretion and the processes that cause such rapid and intense outbursts. What makes these outbursts even more fascinating is the fact that they are not always predictable. The object has shown erratic behavior with periods of intense activity followed by quieter phases. This unpredictability challenges our models of black hole behavior and opens up new avenues for research. Scientists are particularly interested in the cause of these outbursts. They believe the energy released during these bursts is tied to the dynamics of the accretion disk and the magnetic field surrounding the black hole. As matter from the companion star is drawn in, the rotation of the material creates friction and heat, causing the material to emit energy. The magnetic fields, which are believed to be incredibly strong around the black hole, play a crucial role in directing this energy into powerful jets of radiation. These jets, which can be seen as beams of energy shooting out from the poles of the black hole, provide further insight into the processes occurring at the heart of the system. The behavior of this object also offers a glimpse into the larger question of how black holes influence the formation and evolution of galaxies. The release of energy from such a black hole can have significant effects on the surrounding space, including the interstellar gas and dust. Understanding how such active black holes interact with their environment is essential for understanding the role of black holes in the broader context of cosmic evolution. This unique object lies at the intersection of stellar mass black holes and extreme activity. It has provided astronomers with a rich source of data, allowing them to test and refine models of black hole behavior. As our observational technology improves, the hope is that we will continue to uncover new insights into the nature of black holes and their role in shaping the universe. The ongoing study of such active black holes represents a critical piece of the puzzle in understanding the most extreme phenomena in the cosmos. With each observation, we come closer to answering some of the deepest questions in astrophysics. What happens at the event horizon of a black hole? How does a black hole's immense gravitational pull affect its surroundings? And what can the behavior of active black holes tell us about the formation and evolution of galaxies? As we continue to observe and analyze this object, these questions will drive our exploration into the mysterious, powerful world of black holes. The positioning of V404 Cygni within the Milky Way galaxy is crucial to understanding its significance. Located about 7,800 light-years from Earth in the constellation Cygnus, it resides in the dense star fields of the Milky Way's disk. The black hole is situated near the plane of the galaxy, where stars are densely packed and the cosmic environment is ripe for interactions. The region surrounding V404 Cygni is populated with other stars and remnants of supernovae, all within the complex web of gravitational forces that shape the galaxy. This central location gives V404 Cygni a pivotal role within its immediate galactic neighborhood. However, while the black hole's environment is critical to its function, its distance from Earth also plays a part in how we study it. Though relatively far away, its brightness and activity make it a standout object in observational studies. At 7,800 light-years, V404 Cygni is far enough to avoid posing any threat to Earth, but close enough to provide a valuable opportunity for study. The distance from Earth does not hinder the ability to observe the black hole's emissions. Modern observatories such as the Chandra X-ray Observatory and the Swift satellite allow astronomers to detect and analyze the X-ray bursts emitted from V404 Cygni with unprecedented clarity. These instruments are specifically designed to observe high-energy radiation, allowing scientists to study the interactions between the black hole and its surrounding environment. The black hole's powerful X-ray outbursts, some of the brightest seen in the galaxy, can be traced back to the accretion process material from its companion star spirals inward, forming a glowing accretion disk that generates intense radiation. These observations not only provide a direct view of the black hole's behavior, but also reveal important details about the dynamics of accretion and the underlying processes that drive such powerful emissions. V404. Cygni's position in the galaxy is not just defined by its location in Cygnus, but by the unique relationship it shares with its companion star. The binary system itself is relatively close compared to other systems of its kind, making it an ideal target for study. Its proximity gives scientists the rare opportunity to study a black hole that is actively feeding, which can reveal insights into how such objects behave in real time. The interaction between the black hole and the companion star is crucial to the overall dynamics of the system. As the black hole pulls material from the star, it influences the star's evolution, altering the behavior of both celestial bodies in a continuous cycle. This feeding process, known as accretion, results in the formation of a hot glowing accretion disk around the black hole. The material within this disk heats up as it spirals inward, emitting powerful X-rays and gamma rays in the process. The amount of material being fed into the black hole directly impacts the intensity of the radiation emitted, and this process is what drives the spectacular outbursts that make V404 Cygni so unique. The binary nature of this system introduces a level of complexity that is absent in isolated black holes. The accretion disk formed by the interaction of the black hole and its companion star is not a stable, constant feature. Instead, it fluctuates over time depending on the rate at which the black hole consumes material. These fluctuations are responsible for the erratic nature of the X-ray bursts emitted by V404 Cygni. Sometimes the outbursts are incredibly bright, temporarily outshining the light of the surrounding stars. At other times, the system quiets down with only faint emissions detectable. These changes in intensity are part of what makes studying V404 Cygni so challenging. While the overall behavior of the system follows certain patterns, predicting the exact timing and intensity of the outbursts is still beyond our current capabilities. This unpredictability continues to pose challenges to scientists, but it also drives further investigation into the mechanisms behind black hole activity. In terms of its effect on the surrounding space, the intense radiation emitted by V404 Cygni has a far-reaching impact. The X-ray bursts produced by the black hole can influence the interstellar medium, the gas and dust that fill the spaces between stars. As the radiation interacts with this material, it can cause ionization, heating, and even the ejection of particles into space. This process helps to shape the environment around the black hole, contributing to the larger cosmic ecosystem in which it exists. The power of the radiation released by V404 Cygni is not limited to the immediate vicinity of the black hole. It extends outward, affecting the entire region of space around it. The influence of such a powerful object can even play a role in the formation of new stars, as the material within the interstellar medium is impacted by the energetic emissions of the black hole. Despite the challenges posed by its unpredictable nature, V404 Cygni provides a unique opportunity to study the behavior of active black holes. It offers a glimpse into the processes that occur at the event horizon, the point beyond which nothing, not even light, can escape. By studying this object, scientists can learn more about how matter behaves, when it is caught in the immense gravitational pull of a black hole. The material within the accretion disk, for example, reaches temperatures high enough to produce X-rays, allowing astronomers to detect and analyze these emissions. Understanding the dynamics of this material can provide insights into the fundamental physics of black holes and accretion, including the role of magnetic fields and the processes that lead to the formation of powerful jets of radiation. These insights could have far-reaching implications for our understanding of the universe, particularly when it comes to the behavior of objects at the extreme end of the spectrum of mass and gravity. As technology continues to advance, our ability to observe and understand active black holes, like V404 Cygni, will only improve. The precision of current instruments allows for more detailed observations than ever before, and as new technologies emerge, the hope is that we'll be able to answer some of the most fundamental questions about black holes. How do they influence their environment? What is the precise mechanism behind the X-ray outbursts? And what can the behavior of black holes tell us about the larger processes of cosmic evolution? The study of V404 Cygni is an ongoing journey, one that will continue to yield valuable insights into the nature of black holes and their role in the universe. With each new discovery, we move closer to understanding one of the most fascinating and enigmatic phenomena in all of astrophysics. The characteristics of a black hole, though elusive, are critical in understanding how these cosmic objects operate. At the core of V404 Cygni lies a dense region of space where gravity is so strong that not even light can escape. This region is known as the event horizon, which marks the point of no return. Once something crosses this boundary, it is irrevocably drawn into the black hole, unable to escape. The event horizon itself is not a solid surface, but rather a boundary, where the escape velocity equals the speed of light. This means that any light or matter that approaches too closely to the black hole is consumed by its gravitational pull, disappearing from the observable universe. This creates a region of space that to us appears as a perfect void, one that cannot be seen directly. What happens inside the event horizon is unknown, as our current understanding of physics breaks down under such extreme conditions. In addition to the event horizon, a black hole like V404 Cygni possesses what is known as a singularity. This is a point at the center of the black hole where gravity becomes infinite and the laws of physics as we know them no longer hold. The singularity represents the end of the path for matter and light, as everything gets compressed into an infinitely small space. This idea is a key component of general relativity, the theory developed by Albert Einstein to explain how gravity works on large scales. According to general relativity, the singularity is the point where space-time curves infinitely, and all known physics ceases to function as we understand it. However, the singularity itself cannot be observed directly as it lies within the event horizon beyond the reach of any observational instruments. What happens at the singularity remains one of the greatest mysteries in astrophysics. Despite the lack of direct observation of the interior of black holes, scientists can study the effects of black holes on their surroundings. The accretion disk that forms around a black hole plays a crucial role in this process. The disk is made up of gas dust and other material that is drawn toward the black hole. As this material spirals inward, it is heated to extremely high temperatures, emitting large amounts of radiation, including X-rays, gamma rays, and ultraviolet light. This radiation is often detectable by astronomers, providing us with valuable information about the black hole's behavior. The material within the accretion disk is also subject to extreme gravitational forces. These forces cause the material to accelerate as it approaches the event horizon, and as it does, it begins to release energy in the form of radiation. The higher the speed of the material, the greater the energy it releases. This process can cause bursts of X-rays to be emitted which can be observed across vast distances. These X-ray bursts are some of the brightest objects in the universe and provide a means for astronomers to study the properties of black holes and their accretion disks. The magnetic fields surrounding a black hole also play a significant role in its behavior. As material spirals into the black hole, it interacts with these magnetic fields, which can be incredibly strong. These magnetic fields are believed to be responsible for generating the powerful jets of energy that are sometimes observed emanating from the poles of the black hole. These jets can extend for thousands of light years and are one of the most dramatic phenomena associated with black holes. They are composed of particles that are accelerated to nearly the speed of light, and as they travel through space, they release vast amounts of radiation. These jets provide further insight into the complex environments surrounding black holes and are an essential component of our understanding of how black holes influence the universe. V404 Cygni's activity, particularly its X-ray bursts, has allowed astronomers to study the structure and dynamics of its accretion disk in great detail. These observations are particularly important because they offer insight into the behavior of matter as it approaches a black hole. The variability of the X-ray emissions from V404 Cygni has given scientists valuable clues about the accretion process and the mechanisms that drive these powerful outbursts. By studying the way the X-rays fluctuate, astronomers can learn more about the density, temperature, and composition of the material in the accretion disk. The variability in these bursts also provides information about the magnetic fields around the black hole and how they influence the behavior of the material in the disk. The rapid fluctuations in V404 Cygni's X-ray emissions are thought to be caused by the complex interaction between the accretion disk and the magnetic fields surrounding the black hole. As material spirals inward, it becomes subject to intense friction and pressure, which causes it to heat up and emit radiation. The strength of the magnetic fields determines how this radiation is distributed and whether it is emitted in bursts or in a more steady stream. These fluctuations in brightness are not fully understood, but they offer valuable clues about the dynamics of black holes and the accretion process. One of the main goals of current research is to understand how these bursts are triggered and why they occur so unpredictably. Scientists are particularly interested in whether the bursts are caused by changes in the accretion rate variations in the magnetic fields, or some combination of these factors. Understanding these processes will be key to unlocking the mysteries of black hole behavior. The study of black holes like V404 Cygni also raises important questions about the fundamental nature of space and time. The extreme gravity of a black hole distorts space-time in ways that are difficult to comprehend. This distortion is so intense that it can slow down time itself. To an outside observer, time appears to slow down as objects approach the event horizon. This phenomenon, known as gravitational time dilation, occurs because the intense gravity of the black hole warps the fabric of space-time. As an object gets closer to the event horizon, the flow of time appears to slow down relative to the rest of the universe. This effect, predicted by Einstein's theory of general relativity, has been confirmed through various experiments and observations. It is a powerful reminder of just how different the environment around a black hole is from our own, and how extreme the gravitational forces can be. V404 Cygni exists within a binary system, a pairing of two celestial bodies bound together by gravity. In this system, a massive star orbits around a stellar mass black hole. The interaction between these two bodies is central to understanding the behavior of V404 Cygni, as the gravitational pull of the black hole causes the companion star to lose material. This material is drawn toward the black hole in a process known as accretion, where it forms a spinning heated disk of gas and dust around the event horizon. As the material spirals inward, it accelerates, becoming intensely heated and emitting powerful radiation across multiple wavelengths from radio waves to X-rays. The dynamics of this accretion process are crucial to the black hole's activity. The accretion disk is not a static structure but a highly dynamic one, with the material constantly moving and interacting with the black hole's gravitational field. The material in the disk, which includes gas dust and even stellar remnants, is torn apart by the immense forces at play. The intense heat generated by this friction leads to the production of bright X-rays which can be observed across vast distances. The companion star in this binary system plays a vital role in maintaining the activity of V404 Cygni. As the star loses material to the black hole, its structure is gradually altered. The rate at which the black hole feeds on the star's material fluctuates over time, influencing the brightness and frequency of the X-ray bursts emitted by the system. When the star is in close proximity to the black hole, the gravitational interaction becomes more intense, leading to greater material loss. This loss of mass can significantly affect the star's lifespan and its evolution, as the material stripped away from the star is no longer available to sustain its energy production. The relationship between the black hole and the companion star is not simply one of predation, but of mutual influence where the feeding process alters both bodies in significant ways. The star's life is shortened by the mass it loses, while the black hole becomes more active as it draws in the material, intensifying its energy emissions. Over time, these processes will cause the binary system to evolve, possibly leading to the eventual end of the companion star's life and a change in the dynamics of the system. As the material from the companion star falls into the black hole, it forms the accretion disk, a turbulent, rapidly rotating mass of gas. The material within this disk becomes extremely hot-heated to millions of degrees by the friction and gravitational forces at play. This intense heat causes the material to emit radiation in the form of X-rays and other high-energy electromagnetic waves. The process of accretion is not always steady, and fluctuations in the accretion rate can lead to bursts of energy. These bursts are what make V404 Cygni so interesting to astronomers. The black hole's outbursts are not consistent, but occur in unpredictable intervals, making the system a dynamic and challenging target for study. These bursts can be extremely bright, briefly outshining entire galaxies before dimming again. The mechanisms that drive these bursts are still not fully understood, but they are thought to be linked to changes in the accretion rate variations in the magnetic fields and the instability of the accretion disk itself. The accretion disk around V404 Cygni is not a uniform smooth disk, but is instead a chaotic structure. The material in the disk moves at varying speeds, with some regions moving faster than others. This difference in velocity creates turbulent conditions, which can lead to the formation of shocks within the disk. These shocks, combined with the intense magnetic fields around the black hole, contribute to the unpredictable nature of the X-ray bursts. In addition to the X-rays produced by the accretion disk, V404 Cygni also emits powerful jets of particles and radiation from its poles. These jets are thought to be powered by the strong magnetic fields around the black hole. The material in the accretion disk, influenced by the black hole's magnetic field, is ejected along the rotational axis in narrow, focused beams. These jets can extend for thousands of light-years, carrying with them immense amounts of energy and particles at near light speed. They are one of the most striking features of active black holes and provide valuable information about the magnetic fields and material dynamics around the black hole. V404 Cygni's binary system also influences the behavior of the surrounding space. The material being pulled from the companion star and feeding into the black hole has an impact on the interstellar medium, the gas and dust that fill the spaces between stars. As the material from the star is drawn toward the black hole, it interacts with the surrounding gas, ionizing it and releasing large amounts of radiation. This process has a feedback effect as the energy produced by the black hole can heat up the interstellar medium, causing it to expand and potentially affect the formation of new stars. The radiation from the black hole can also influence nearby molecular clouds, which are the birthplaces of new stars. In this way, V404 Cygni's activity does not just affect its immediate surroundings, but can have a broader impact on the evolution of the region. The companion star in the system, though, being slowly consumed by the black hole, also undergoes changes due to its proximity to the black hole. The star's outer layers are stripped away, and the material lost to the black hole is gradually replaced by the star's inner layers, which are pulled in. Over time, this process can alter the star's composition, leading to significant changes in its structure and energy production. The eventual fate of the companion star is uncertain, but it is likely that it will eventually be consumed entirely by the black hole, leaving only the black hole behind. This process is a dramatic and destructive one, but it is also a common feature in the evolution of binary systems with black holes. The end of the star's life, marked by its consumption by the black hole, will also mark the end of the current dynamics in the system. The binary system may eventually evolve into a single black hole, and the behavior of the system will shift accordingly. The feeding process in the binary system between the black hole and the companion star provides valuable insight into the behavior of black holes in a dynamic environment. This interaction drives the activity of the black hole, producing the X-ray bursts and jets of radiation that make V404 Cygni such an interesting object of study. Understanding the accretion process and the influence of the magnetic fields around the black hole will help scientists learn more about the mechanisms at play in the most extreme environments of the universe. As technology continues to improve, future observations of V404 Cygni and similar systems will likely yield even more detailed data, further enhancing our understanding of these cosmic objects. The accretion disk surrounding V404 Cygni is a critical feature in understanding its behavior. This disk is formed by material stripped from the companion star, which is pulled toward the black hole by its immense gravitational force. As the material spirals inward, it is accelerated and heated to extreme temperatures due to the friction between particles within the disk. The heating process causes the material to emit vast amounts of radiation, including X-rays, which can be detected by space-based telescopes. This radiation is one of the primary ways in which astronomers study the properties of black holes, as it provides a direct link to the processes occurring around the event horizon. The intense heat within the accretion disk can reach temperatures of millions of degrees far hotter than the surface of the Sun, and the energy emitted by the disk can temporarily outshine entire galaxies. The accretion disk is not a simple uniform structure but a dynamic system with varying levels of density and temperature. As material falls toward the black hole, it forms a rotating disk that moves in a spiral pattern, with the inner regions moving faster than the outer regions. This rotation of the accretion disk creates a turbulent environment. The material within the disk is constantly interacting with itself, resulting in areas of higher and lower density. This turbulence can lead to the formation of shock waves within the disk, which release additional energy. These shock waves contribute to the unpredictable nature of the X-ray bursts observed from V404 Cygni. The rapid variability in the brightness of these bursts is thought to be a result of fluctuations within the accretion disk, caused by changes in the rate at which material is being pulled into the black hole. These fluctuations are not entirely understood, but are believed to be related to the magnetic field surrounding the black hole and the dynamics of the accretion process. The strong magnetic fields around V404 Cygni also play a crucial role in the behavior of the accretion disk. These magnetic fields are thought to be generated by the motion of charged particles within the disk, particularly as material spirals inward toward the black hole. The magnetic fields can influence the motion of the particles in the disk, causing them to align in specific patterns. In some cases, these fields become twisted, and the material within the disk is accelerated along magnetic field lines, resulting in the formation of powerful jets of energy. These jets, which extend from the poles of the black hole, are a key feature of active black holes like V404 Cygni. They are made up of high-energy particles that travel at relativistic speeds approaching the speed of light and can extend for thousands of light years. The exact mechanism behind the formation of these jets is still a topic of active research, but it is believed that they are powered by the magnetic field surrounding the black hole. The interaction between the accretion disk and the magnetic fields around V404 Cygni leads to the release of energy in the form of both X-rays and the aforementioned jets. The X-rays are produced as the material in the accretion disk is heated to extreme temperatures by the gravitational forces at play, while the jets are generated by the acceleration of charged particles along magnetic field lines. These processes create a highly energetic and dynamic environment around the black hole, with emissions that can be observed across vast distances. The study of these emissions provides astronomers with valuable information about the structure of the accretion disk, the nature of the magnetic fields, and the behavior of material in the vicinity of a black hole. The size and shape of the accretion disk are influenced by a variety of factors, including the rate at which material is being drawn into the black hole and the properties of the companion star. In some cases, the accretion disk can become unstable, leading to fluctuations in the amount of material being accreted. These fluctuations are responsible for the dramatic X-ray outbursts observed from V404 Cygni. During periods of high activity, the accretion disk becomes highly luminous, emitting vast amounts of energy in the form of X-rays. These bursts of energy are often brief but can be extremely bright, temporarily outshining entire galaxies. The study of these outbursts is critical for understanding the dynamics of accretion and the role of magnetic fields in powering the emissions from the black hole. The presence of the companion star in the binary system also has a direct impact on the behavior of the accretion disk. The material stripped from the star by the black hole provides the fuel for the disk, but the rate at which this material is accreted can vary over time. Changes in the companion star's behavior, such as variations in its mass loss rate or the structure of its outer layers, can lead to changes in the dynamics of the accretion disk. These changes in turn affect the X-ray bursts and the overall activity of the system. In some cases, the material being pulled from the star may accumulate in the outer regions of the disk, where it can be compressed and heated before being pulled into the black hole. This accumulation of material can lead to a temporary increase in the luminosity of the system, creating a bright X-ray flare. One of the most striking features of V404 Cygni's accretion disk is its variability. Unlike many other black holes which remain relatively stable, V404 Cygni exhibits rapid changes in its X-ray emissions, often on timescales of hours or days. This variability makes the system particularly interesting to astronomers, as it provides a window into the complex processes occurring within the accretion disk. Understanding the causes of this variability is one of the key challenges in black hole research. The fluctuations in brightness are likely a result of both the dynamics of the accretion disk and the behavior of the magnetic field surrounding the black hole. As material is pulled into the black hole, the disk becomes unstable, and the release of energy can vary significantly depending on the conditions within the system. In addition to the X-rays emitted by the accretion disk, the study of the jets produced by V404 Cygni provides further insight into the behavior of the system. These jets are thought to be powered by the interaction between the accretion disk and the black hole's magnetic field. As the material in the disk is accelerated along magnetic field lines, it is ejected from the black hole's poles at relativistic speeds, creating a beam of high-energy particles that extends for vast distances. These jets are one of the most dramatic features of active black holes, and their study offers valuable clues about the role of magnetic fields in black hole physics. The X-ray outbursts emitted by V404 Cygni are one of its most remarkable and intriguing features. These bursts are the result of the rapid accretion of material from the companion star, which spirals inward toward the black hole. As this material enters the accretion disk, it is subjected to extreme gravitational and frictional forces, causing it to heat up to millions of degrees. This intense heat generates high-energy radiation, including X-rays, which are the most noticeable emissions from the system. The X-ray bursts are incredibly bright and can temporarily outshine entire galaxies, making them one of the most noticeable phenomena in the universe. These bursts are not constant but vary greatly in intensity, often changing on timescales of hours or days. The irregularity of these bursts is what makes V404 Cygni particularly fascinating to astronomers. The X-ray outbursts from V404 Cygni are thought to be driven by changes in the rate of material falling into the black hole. When the accretion rate increases, more material is funneled into the black hole, causing the accretion disk to become more luminous. This results in an increase in the X-ray emissions, often leading to dramatic bursts of radiation. The exact cause of these fluctuations in the accretion rate is still a topic of active research. It is believed that the accretion disk can become unstable, at times leading to variations in the amount of material being drawn toward the black hole. These instabilities are likely linked to changes in the magnetic fields around the black hole, which influence the flow of material in the accretion disk. In addition to the fluctuations in the accretion rate, the X-ray bursts from V404 Cygni are also influenced by the structure of the accretion disk itself. The disk is not a simple uniform structure, but is highly dynamic with varying levels of density and temperature. The inner regions of the disk, which are closer to the black hole, move much faster than the outer regions, leading to a gradient of velocities within the disk. This difference in velocity creates a turbulent environment, which can result in the formation of shock waves within the disk. These shock waves can cause dramatic bursts of X-rays, which are observed as brief, intense outbursts. The complexity of the accretion disk is one of the reasons why the X-ray emissions from V404 Cygni are so variable. The rapid variability of the X-ray bursts from V404 Cygni is one of the key aspects of its behavior that makes it an intriguing target for study. These bursts can occur on timescales as short as hours or even minutes, making them one of the most rapidly changing phenomena in the universe. The bursts are thought to be triggered by changes in the dynamics of the accretion disk, which can result from a variety of factors including changes in the magnetic field, the rate of accretion, and the internal structure of the disk itself. The unpredictability of these bursts has made it difficult to model the behavior of V404 Cygni accurately, but advances in observational technology are helping to improve our understanding of these processes. The X-ray emissions from V404 Cygni are not only an important tool for studying the black hole itself, but also provide insight into the behavior of the surrounding environment. The radiation emitted by the black hole can have a significant impact on the interstellar medium, the gas and dust that fills the space between stars. As the X-rays interact with this material, they can ionize it, heating it up and causing it to expand. This process can affect the local environment around the black hole, altering the density and temperature of the surrounding gas. The release of energy from the black hole can also influence the formation of new stars, as the heated gas can trigger the collapse of nearby molecular clouds. In this way, the X-ray bursts from V404 Cygni are not only a result of the black hole's accretion process, but also play a role in shaping the environment around it. In addition to the X-rays, V404 Cygni also produces gamma rays, which are even higher in energy. These gamma rays are thought to be generated by the same processes that produce the X-rays, but they are emitted from the outer regions of the accretion disk, where the material is still in the process of being accelerated. The gamma rays are typically harder to detect than the X-rays, but recent advances in gamma ray observatories have allowed astronomers to study these emissions in greater detail. The gamma rays emitted by V404 Cygni provide further insight into the dynamics of the accretion disk and the role of magnetic fields in powering the system. The study of V404 Cygni's X-ray bursts and gamma ray emissions has led to important breakthroughs in our understanding of black holes and their behavior. By observing the fluctuations in the X-ray emissions, astronomers can gain valuable information about the structure and dynamics of the accretion disk. The rapid variability of the X-rays provides clues about the internal processes occurring within the disk, including the role of magnetic fields and the behavior of the material as it spirals inward toward the black hole. These observations also provide insight into the complex interaction between the black hole and its companion star. As material is stripped from the star, it feeds into the black hole, causing the system to become highly active. The X-ray bursts observed from V404 Cygni are a direct result of this process and provide valuable information about how black holes interact with their environment. The unpredictable nature of the X-ray burst from V404 Cygni makes it an ideal candidate for studying the behavior of active black holes. Unlike many other black holes which remain relatively stable, V404 Cygni exhibits rapid changes in its emissions, providing a glimpse into the complex processes that drive these bursts of energy. The ongoing study of V404 Cygni's X-ray bursts will continue to shed light on the inner workings of black holes and help refine our models of accretion and black hole dynamics. As new observational techniques and technologies are developed, the hope is that we will gain an even deeper understanding of the complex behavior of these fascinating objects and the role they play in shaping the universe. The cause of the X-ray outbursts observed from V404 Cygni remains a topic of ongoing research, but several factors are believed to contribute to these extraordinary emissions. The central cause is the accretion process itself, in which material from the companion star is drawn toward the black hole. This material spirals into the black hole, forming an accretion disk around it. As the material falls inward, the intense gravitational forces at play cause it to heat up to millions of degrees, emitting radiation in the process. This radiation includes X-rays, which can be detected from Earth. However, the variability of the X-ray bursts is not solely due to the accretion process. Scientists believe that the magnetic fields around the black hole play a crucial role in the intensity and frequency of the outbursts. These magnetic fields, which are generated by the motion of charged particles within the accretion disk, can influence the flow of material and cause the release of bursts of energy. The strength and configuration of the magnetic fields are believed to determine how the material in the accretion disk behaves and how the energy is released as X-rays. Another key factor in the outbursts is the rate at which material is being accreted onto the black hole. The amount of material in the accretion disk fluctuates over time, which can lead to changes in the intensity of the X-ray emissions. During periods of high accretion, more material is drawn into the black hole, causing the system to become more luminous. This leads to brighter X-ray bursts, which can sometimes outshine the surrounding stars. Conversely, during periods of lower accretion, the X-ray emissions diminish and the system quiets down. These fluctuations in the accretion rate are thought to be caused by a combination of factors, including the star's behavior, the magnetic fields around the black hole, and the internal dynamics of the accretion disk itself. The variability of the X-ray bursts is one of the defining features of V404 Cygni's behavior. Unlike many other black holes which produce steady emissions, V404 Cygni exhibits rapid changes in brightness, sometimes on timescales as short as hours or even minutes. These fluctuations make the system particularly interesting to astronomers, as they provide a glimpse into the complex and dynamic processes occurring around the black hole. The unpredictability of the bursts is also a challenge for scientists, as it makes it difficult to predict when the system will enter a period of high activity. However, this variability also makes V404 Cygni an ideal target for study, as each outburst provides valuable data that can be used to refine our models of black hole behavior. One of the most intriguing aspects of the X-ray outburst from V404 Cygni is their connection to the accretion disk. The material in the disk is constantly interacting with itself, leading to fluctuations in the density and temperature of the disk. These fluctuations create a turbulent environment that can cause shock waves within the disk. These shock waves in turn generate bursts of X-rays, which are observed as sudden increases in brightness. The interaction between the magnetic fields and the accretion disk also plays a role in the generation of these bursts. As the material in the disk moves inward, it can become twisted by the magnetic fields, which accelerates the material and generates high-energy radiation. The combination of turbulent shock waves and magnetic fields results in the unpredictable nature of the X-ray emissions. In addition to the X-rays, V404 Cygni also produces gamma rays, which are even higher in energy. These gamma rays are thought to be emitted from the outer regions of the accretion disk, where the material is still in the process of being accelerated. The gamma rays are typically more difficult to detect than the X-rays, but recent advances in gamma-ray observatories have allowed scientists to observe these emissions in greater detail. The gamma rays provide additional insights into the dynamics of the accretion disk and the role of magnetic fields in powering the system. By studying both the X-rays and gamma rays, astronomers are able to gain a more complete picture of the processes occurring around the black hole. The X-ray bursts from V404 Cygni are also influenced by the physical structure of the accretion disk. As the material in the disk spirals inward, it forms a rotating structure, with the inner regions of the disk moving much faster than the outer regions. This difference in velocity creates a gradient of speeds within the disk, which leads to turbulent interactions between the material. The turbulence can cause areas of higher density to form within the disk, which in turn leads to the creation of shock waves. These shock waves contribute to the dramatic bursts of X-rays that are observed from V404 Cygni. The complex structure of the accretion disk and the way in which the material moves within it are key to understanding the behavior of the system and the cause of the X-ray bursts. As the material falls toward the black hole, it passes through increasingly hotter regions of the accretion disk. This heating occurs due to the friction between particles in the disk, as well as the intense gravitational forces exerted by the black hole. As the material is compressed and heated, it emits radiation which can be observed as X-rays. The closer the material gets to the event horizon, the hotter and more energetic it becomes, producing brighter bursts of radiation. The variability of these bursts is linked to the changing dynamics within the accretion disk. The fluctuations in the rate at which material is being accreted, as well as the behavior of the magnetic fields around the black hole, contribute to the unpredictability of the X-ray emissions. Understanding these processes is essential for explaining the complex and dynamic behavior of active black holes, like V404 Cygni. The study of V404 Cygni's X-ray bursts has provided astronomers with valuable information about the accretion process and the role of magnetic fields in powering the system. The variability of the bursts has helped to refine our understanding of how material behaves in the intense gravitational environment around a black hole. By observing these bursts in detail, scientists are gaining insights into the underlying physics of black holes and the complex interactions between the accretion disk, the magnetic fields, and the black hole itself. As our observational technology continues to improve, we can expect to gain even more detailed information about the nature of these X-ray bursts and the processes that drive them. The unpredictability of V404 Cygni's outbursts presents a unique challenge for scientists, but it also provides a rare opportunity to study the most extreme environments in the universe. With each new observation, we learn more about the inner workings of black holes and the forces that shape their behavior. These insights not only help us to better understand black holes, but also contribute to our broader knowledge of the universe and the physical processes that govern it. The ongoing study of V404 Cygni will continue to shape our understanding of black holes and may lead to new discoveries that challenge our current models of astrophysics. The energy emissions from V404 Cygni span a remarkable range across the electromagnetic spectrum from radio waves to visible light X-rays and gamma rays. Each type of radiation provides a different perspective on the processes unfolding near the black hole, and together they paint a detailed picture of one of the most active binary systems in the Milky Way. The most intense emissions occur in the X-ray and gamma-ray ranges, but lower energy radiation such as visible and radio waves are also present, produced by different regions of the system. The inner parts of the accretion disk are responsible for the highest energy emissions, while the outer regions and the jets contribute to the lower energy radiation that can sometimes be observed from Earth. The combination of these emissions creates a multi-layered environment of extreme energy and dynamic interactions. The X-rays emitted by V404 Cygni are the most prominent and have been the focus of extensive observation. These rays originate from the innermost region of the accretion disk, where material is heated to millions of degrees as it spirals toward the event horizon. The process of heating and radiation is not uniform, leading to sudden bursts of brightness and periods of calm. These variations are closely linked to fluctuations in the amount of material being drawn into the black hole. When the accretion rate increases, the X-ray intensity rises sharply. When it decreases, the system grows dimmer. This constant variability makes V404 Cygni one of the most luminous X-ray sources known within our galaxy. The radiation from these bursts can even interfere with nearby interstellar gas, ionizing and heating it, and in some cases triggering shock waves that ripple through the surrounding environment. Gamma rays represent another extreme in V404 Cygni's emissions. These are generated in the outermost regions of the accretion disk and along the jets that extend outward from the poles of the black hole. The gamma rays result from the acceleration of charged particles to near-light speeds by the magnetic fields that wrap around the system. Observing these gamma rays requires space-based instruments capable of detecting high-energy photons, such as the Fermi Gamma Ray Space Telescope. The study of these emissions has provided astronomers with deeper insight into the conditions near the event horizon and the strength of the magnetic fields involved. Gamma rays also help trace the structure of the jets, offering clues about how these powerful streams are formed and maintained. In addition to X-rays and gamma rays, V404 Cygni emits radiation in the visible and radio wavelengths. During periods of heightened activity, visible light emissions can increase dramatically as the accretion disk heats up, These changes can be detected with ground-based telescopes, allowing astronomers to study the optical behavior of the system alongside its high-energy radiation. The visible light from the system is faint under normal conditions, but becomes more prominent during major outbursts when the disk brightens significantly. These optical observations complement the data from X-ray and gamma-ray telescopes, helping to create a more complete picture of the black hole's energy output. Meanwhile, the radio emissions come from the jets which produce synchrotron radiation as charged particles spiral through the magnetic fields. This type of radiation provides a way to study the motion and structure of the jets over time. The study of V404 Cygni's multi-wavelength emissions has been crucial in revealing the interconnected nature of the processes at work in the system. Each form of radiation traces a different component of the black hole's environment: X-rays from the inner disk, gamma rays from the outer regions, and jets, visible light from the heated disk and companion star, and radio waves from the extended jets. Together they show how energy is transferred and transformed as material moves inward toward the black hole or outward through the jets. The data from these various wavelengths are combined by astronomers to create detailed models of the system's structure and behavior, allowing them to understand how energy flows through the complex interplay of gravity, magnetism, and motion. The emission of such high levels of energy also has broader consequences for the surrounding environment. The radiation and particles expelled by the black hole interact with the interstellar medium, heating nearby gas clouds and altering their composition. The energetic particles carried by the jets can travel vast distances through space, influencing regions far from the black hole itself. In some cases, these interactions can trigger the formation of new stars by compressing nearby molecular clouds. The feedback between the black hole and its surroundings demonstrates how such systems play an active role in the evolution of galaxies, redistributing energy and matter on a cosmic scale. V404 Cygni is therefore not only an object of intrinsic interest, but also a key example of how black holes shape their environments. The periodic bursts of radiation from V404 Cygni also provide an opportunity to test theories of relativity and plasma physics under extreme conditions. The behavior of matter and light near the event horizon can only be understood through the framework of Einstein's general relativity, which predicts how gravity bends light and distorts time. The timing and structure of the X-ray bursts allow scientists to measure these effects indirectly, offering evidence for how space-time behaves in the vicinity of a black hole. Similarly, the dynamics of the accretion disk and the magnetic fields within it help refine our understanding of how plasma, the hot ionized gas that makes up most of the disk, responds to intense gravitational and magnetic forces. Each observation of V404 Cygni thus provides a natural laboratory for studying physics in an environment that cannot be replicated on Earth. Although the high-energy emissions of V404 Cygni can be observed across multiple wavelengths, the system does not emit continuously. It alternates between quiet periods and intense outbursts. During these quiescent phases, the accretion rate slows, and the emissions drop dramatically sometimes to levels that are barely detectable. These intervals of calm are followed by renewed bursts of activity, which may last for weeks or months before subsiding again. This cyclical behavior provides additional insight into the long-term evolution of the system. The reasons behind these cycles are still under investigation, but they likely involve a combination of the magnetic field dynamics, the orbital motion of the companion star, and instabilities in the accretion disk. The balance between these factors determines when the system becomes active and how long each phase lasts. The extraordinary range of energy emissions from V404 Cygni makes it one of the most valuable objects for studying black hole physics. By observing its behavior across different wavelengths, scientists can piece together a comprehensive understanding of how energy is produced, transported, and released near a black hole. Each burst, flare, and pulse of radiation carries with it information about the physical processes at work in one of the most extreme environments in the universe. The ongoing observation of this system continues to refine our understanding of how matter behaves under the influence of gravity and magnetism at their most powerful, bringing us closer to grasping the full complexity of black hole dynamics. The behavior of V404 Cygni over time reveals an extraordinary pattern of variability that distinguishes it from many other known black holes. Unlike systems that remain relatively steady in their emissions, this object demonstrates long periods of quiet followed by dramatic bursts of activity. These transitions between dormant and active phases occur over spans of years or even decades, each new outburst serving as a reminder of the powerful processes still unfolding deep within the system. Historical records show that V404 Cygni's most intense outbursts have been observed roughly once every few decades, with notable episodes recorded in 1938, 1956, 1989, and 2015. Each of these events was marked by a sudden and dramatic increase in brightness across multiple wavelengths, indicating a surge in the rate of material being accreted by the black hole. During such events, the system can become one of the brightest X-ray sources in the sky, briefly outshining all other known black holes in the Milky Way. The intervals between these eruptions are filled with years of relative quiet, during which the accretion rate drops and the system becomes faint. This cyclical behavior suggests a recurring process in which the material from the companion star accumulates over time before collapsing inward in a rapid explosive feeding episode. These cycles are believed to be governed by changes in the stability of the accretion disk. During the quiet periods, the flow of material from the companion star continues, but at a slower rate, allowing gas to build up in the outer regions of the disk. Over time, the accumulated material becomes dense and hot enough to trigger an instability that causes it to rush inward toward the black hole. This sudden influx of matter leads to a spike in luminosity and the emission of intense radiation, creating the characteristic outbursts that define the system. Once the excess material is consumed, the disk cools and stabilizes, and the system returns to a low luminosity state. The duration and intensity of each phase depend on factors such as the rate of mass transfer from the companion star, the temperature of the accretion disk, and the strength of the magnetic fields influencing the flow of material. This complex interplay of factors ensures that no two outbursts are exactly alike, each revealing slightly different details about the inner workings of the system. The 1989 outburst was the first to be observed with modern X-ray and optical instruments, providing a wealth of data that transformed our understanding of stellar mass black holes. During this event, astronomers detected intense bursts of X-rays, visible light and radio emissions that varied on timescales as short as minutes. The light curves graphs showing the intensity of the radiation over time displayed rapid oscillations suggesting that the accretion disk was undergoing violent fluctuations. These variations were among the first direct pieces of evidence that the material near a black hole is not static, but constantly shifting and evolving. The 2015 outburst, observed with even more advanced instruments, confirmed many of these findings and revealed additional layers of complexity. During this event, the system exhibited rapid flares that rose and faded within seconds, accompanied by the ejection of relativistic jets visible in radio wavelengths. The combination of X-ray and radio observations provided strong evidence that the fluctuations in the accretion disk were linked to the launching of the jets, highlighting the deep connection between these two phenomena. Between these periods of high activity, V404 Cygni spends most of its time in a quiescent state. During these intervals, the emissions are faint but steady, allowing astronomers to study the residual accretion flow and the behavior of the companion star. Observations during quiescence have shown that the accretion disk never completely disappears. Instead, it continues to feed the black hole at a much slower rate. The material in the disk becomes cooler and less dense, emitting primarily in optical and radio wavelengths rather than X-rays. The study of these low luminosity phases is just as important as the observation of the outbursts, as it helps scientists understand the full life cycle of the system. By comparing data from active and quiescent periods, researchers can track how the accretion rate, disk temperature, and jet activity evolve over time. The long-term monitoring of V404 Cygni has also revealed changes in its overall behavior that may reflect the gradual evolution of the system. As the companion star continues to lose mass to the black hole, the dynamics of the system are slowly altered. The star's outer layers become thinner, and the gravitational balance between the two objects shifts. Over time, this process may lead to a decrease in the frequency or intensity of the outbursts, although the precise trajectory of the system remains uncertain. The exchange of material between the two bodies also affects their orbital parameters. As mass is transferred, the orbit of the companion star can gradually change, becoming either more circular or more elliptical, depending on the rate and direction of the mass transfer. These subtle shifts can influence how efficiently material is accreted and may play a role in the long-term variability of the system. The variability of V404 Cygni has broader implications for the study of black holes in general. By tracking its changes over time, astronomers can test theoretical models of accretion and jet formation under different conditions. The data from decades of observation have provided crucial evidence that accretion disks are inherently unstable, and that magnetic fields play a central role in regulating their behavior. The ability to observe these changes in real time has made V404 Cygni a cornerstone for understanding how energy is generated and released near black holes. Its frequent outbursts offer rare opportunities to study the transition between different states of accretion, from low luminosity steady phases to high energy explosive ones. Each cycle provides new information about the thresholds at which these transitions occur and the physical mechanisms driving them. As technology continues to advance, future observations will allow scientists to track V404 Cygni's activity with even greater precision. Space-based telescopes designed to monitor X-rays and gamma rays will continue to capture data from the next generation of outbursts, while ground-based optical and radio observatories will provide complementary information about the broader environment of the system. Together, these observations will help refine models of black hole accretion and improve our understanding of the life cycles of binary systems. The study of V404 Cygni's long-term behavior is not just about a single object. It provides a window into the dynamic processes that govern many similar systems across the galaxy. Each burst of energy, each period of quiet, and each shift in luminosity contributes to a growing body of knowledge about how black holes feed, evolve, and interact with the universe around them. The role of V404 Cygni in galactic evolution extends beyond its immediate environment, as the processes occurring around it mirror those that influence galaxies on much larger scales. The immense energy released by the system through X-rays, gamma rays, and jets of charged particles contributes to the redistribution of matter and energy within the Milky Way. These emissions interact with the interstellar medium, the vast expanse of gas and dust that fills the spaces between stars, altering its temperature composition and motion. The feedback produced by such an active black hole can have long-term consequences for star formation as the radiation and particle jets from the system compress or disperse nearby gas clouds. This process, known as black hole feedback, plays an important role in regulating the life cycle of galaxies. Although V404 Cygni is small compared to the supermassive black holes at galactic centers, its local impact offers insight into how these mechanisms operate on both stellar and galactic scales. When energy from the black hole's jets and radiation reaches surrounding interstellar gas, it heats the material and can trigger new waves of star formation. The jets, composed of plasma moving at nearly the speed of light, carry magnetic fields and high-energy particles that can collide with molecular clouds. The compression caused by these impacts can cause parts of the clouds to collapse under their own gravity, leading to the birth of new stars. However, the same energy that stimulates star formation in one region can inhibit it in another. The intense radiation from V404 Cygni can strip electrons from nearby atoms, ionizing the gas and preventing it from cooling enough to form stars. In this way, the system contributes to both the creation and suppression of new stellar generations, acting as both a catalyst and a regulator in the cosmic environment around it. The energy output from V404 Cygni also influences the chemical makeup of its surroundings. As the jets and radiation interact with interstellar material, they drive complex chemical reactions that can alter the abundance of molecules in space. Elements such as carbon, oxygen, and nitrogen are ionized and redistributed by these energetic processes, enriching the surrounding gas with heavier elements produced in earlier generations of stars. This enrichment plays a vital role in the evolution of galaxies as it affects the composition of future stars and planets that will form from this material. Over millions of years, systems like V404 Cygni contribute to the gradual transformation of the interstellar medium, spreading the building blocks of new celestial bodies across the galaxy. The study of V404 Cygni's emissions provides valuable data for understanding the connection between stellar mass black holes and their galactic environments. While supermassive black holes at galactic centers dominate large-scale feedback processes, smaller black holes such as this one offer a closer, more observable example of similar interactions. The physics that governs the jets, magnetic fields, and accretion disks of stellar black holes is remarkably similar to that of their larger counterparts, only on a smaller scale. This similarity allows scientists to use systems like V404 Cygni as models for studying the behavior of more distant and massive black holes. By observing how energy flows through this system, astronomers can infer how supermassive black holes influence the galaxies that host them, providing crucial context for understanding cosmic evolution. Over time, the continuous outflow of energy from V404 Cygni also shapes the structure of its immediate surroundings. The jets carve narrow channels through the interstellar medium, creating elongated cavities filled with ionized gas. These cavities expand slowly over thousands of years as the jets continue to inject energy into them. The resulting structures are sometimes referred to as bubbles or lobes depending on their shape and size. Observations of these features provide evidence of the long-term influence of active black holes on their environments. The jets can extend for light years, meaning that even a relatively small black hole like V404 Cygni can have a measurable effect on its galactic neighborhood over extended periods. The energy released by V404 Cygni is also an important contributor to the diffuse background radiation that fills the galaxy. Every burst of X-rays, every stream of particles, and every flare of gamma rays adds to the cumulative energy distributed throughout the Milky Way. Although the contribution of a single black hole is small compared to the entire galactic output, the combined effect of many such systems creates a complex web of radiation and magnetic fields that pervade the galaxy. This energy shapes the behavior of cosmic rays, high-energy particles that travel through space, and influences the large-scale dynamics of the Milky Way. The presence of active systems like V404 Cygni helps maintain this galactic ecosystem, demonstrating how even small-scale phenomena contribute to the broader structure of the cosmos. Another key aspect of V404 Cygni's influence lies in the interaction between its radiation and dust. The intense X-rays and gamma rays emitted by the system can heat interstellar dust grains, causing them to emit infrared radiation. This reprocessed light allows astronomers to trace the pathways of energy as it moves from the black hole's immediate vicinity into the surrounding space. By studying the infrared emissions produced in this way, scientists can map the distribution of dust and gas around the system and gain insight into how the black hole's activity shapes the interstellar environment. These observations also help refine models of how radiation from black holes affects the temperature and stability of molecular clouds. On a larger timescale, the repeated outbursts from V404 Cygni may influence the long-term evolution of its binary system. Each outburst represents a burst of energy that can alter the orbital parameters of the companion star. As material is transferred from the star to the black hole, the balance of mass in the system shifts, leading to gradual changes in their orbit. Over many millions of years, these changes could alter the distance between the two bodies and the rate at which material is accreted. This slow evolution may ultimately determine the fate of both objects. If the companion star continues to lose material, it may eventually be reduced to a dense core, possibly becoming a white dwarf. Once the supply of material diminishes, the black hole will become less active, entering a long period of quiescence. The system's energy output will fade, leaving behind the remnants of a once turbulent interaction that reshaped its surroundings. V404 Cygni's activity provides a microcosm of processes that occur on a galactic scale. The mechanisms that govern its outbursts, accretion, magnetic fields, and feedback, are the same forces that shape the evolution of entire galaxies. Studying such systems allows astronomers to bridge the gap between stellar and cosmic phenomena, linking the behavior of individual black holes to the grand dynamics of the universe. The data gathered from V404 Cygni thus have implications far beyond a single binary system. They help explain how galaxies grow, how energy is cycled through the cosmos, and how the most extreme objects in existence help sculpt the very fabric of the universe. Through its outbursts, its radiation, and its jets, this small yet immensely powerful system continues to illuminate the interconnectedness of all cosmic structures, from the smallest particles of dust to the largest galactic formations. The first human observations of the system, now known as V404 Cygni, date back long before its true nature was understood. In the early 20th century, astronomers catalogued it as a variable star in the constellation Cygnus, noting irregular fluctuations in brightness that did not match the steady glow of typical stars. At the time, the concept of a black hole existed only as a theoretical idea derived from the equations of general relativity. The observed changes in brightness were attributed to stellar instability, since the notion that an invisible object could consume light and matter had not yet become widely accepted. It would take decades of progress in both theory and technology before the significance of these early observations was fully realized. The periodic bursts of brightness recorded in archival photographic plates from observatories such as Harvard and Mount Wilson hinted at the presence of an energetic system, but the true cause remained hidden behind the limits of the instruments of that era. By the middle of the 20th century, advances in radio and X-ray astronomy began to transform humanity's understanding of the cosmos. the discovery of powerful cosmic X-ray sources revealed that some stars emitted far more energy than nuclear fusion alone could explain. These discoveries laid the groundwork for identifying stellar mass black holes. In 1989, V404 Cygni entered a dramatic outburst phase that changed everything. The system suddenly brightened across the electromagnetic spectrum, becoming one of the most luminous X-ray sources in the sky. Ground-based optical telescopes, X-ray detectors aboard satellites and radio observatories all captured the event simultaneously. For the first time, astronomers were able to study such an outburst in real time using modern instruments. The data gathered during that year confirmed that the object was not a single star, but a binary system containing a black hole. The intense X-ray emissions and rapid variability observed during this event provided clear evidence that matter was being pulled from a companion star into an accretion disk surrounding a massive unseen object. The 1989 event also demonstrated the power of coordinated multi-wavelength observation. Telescopes on Earth and in orbit work together to track the behavior of the system across different energy bands. Optical observations showed dramatic changes in brightness, while X-ray instruments detected rapid bursts of radiation that fluctuated on timescales as short as seconds. Radio telescopes revealed the presence of jets ejecting material into space, offering the first clues about how magnetic fields shape the environment around black holes. This combination of observations marked one of the earliest times that a stellar mass black hole's activity was studied so comprehensively. The data confirmed theoretical predictions about how accretion disks behave and provided evidence that magnetic fields play a central role in directing the flow of material and energy near black holes. Following the 1989 discovery, astronomers continued to monitor the system even during its quieter phases. Observations in the years that followed allowed scientists to refine estimates of the black hole's mass, placing it at roughly 9 times that of the Sun. The companion star was identified as a low-mass object similar to the Sun, but cooler classified as a K-type subgiant. This star orbits the black hole once every 6.5 days, losing material through a gravitational interaction that sustains the accretion disk. By studying the spectrum of the companion star's light, researchers determined that it was being stripped of its outer layers, confirming that it was transferring mass to its partner. This steady loss of material explains the long-term variability of the system and the buildup of energy that leads to periodic outbursts. The outburst of 2015 marked another turning point. Detected simultaneously by space-based observatories such as Swift and Chandra, along with ground-based optical and radio telescopes, it offered an unprecedented level of detail. The system once again erupted with intense X-ray and gamma-ray emissions, accompanied by visible flares that could be observed even with modest amateur telescopes. During this event, astronomers recorded extraordinary variability with bursts of radiation that changed intensity by factors of hundreds within minutes. The radio observations revealed the formation of powerful jets of material that appeared and disappeared rapidly, confirming that the process of accretion and jet ejection is closely linked. This level of activity reinforced V404 Cygni's reputation as one of the most dynamic black hole systems in the Milky Way. The coordination between observatories across the globe during the 2015 outburst represented a new era in time-domain astronomy, the study of how celestial objects change over time. Instruments from multiple continents and orbital platforms combined data in near real time, allowing scientists to piece together a continuous picture of the system's evolution during the event. These observations provided key insights into how matter behaves under the most extreme conditions imaginable. The timing of the bursts, their spectral composition, and their relationship to radio jet activity all helped refine theoretical models of how magnetic fields interact with accreting material. For the first time, the fine details of how a black hole draws in and expels matter were observed with a level of precision previously thought impossible. In addition to these large outbursts, smaller fluctuations have been detected during the system's quieter periods. Sensitive instruments such as the European Space Agency's XMM Newton Observatory and NASA's NuSTAR telescope have recorded faint X-ray flickers that hint at ongoing low-level accretion. These subtle signals are crucial for understanding the full life cycle of the system, showing that the black hole continues to feed even when its emissions are not dramatic enough to attract attention. Observations of the companion star's radial velocity. The change in its motion caused by the gravitational pull of the black hole also allow astronomers to track the orbit precisely. These measurements confirm that the black hole's mass and gravitational influence remain consistent with theoretical expectations for a stellar mass black hole, strengthening the broader understanding of these objects as a population. The accumulation of data from decades of observation has turned V404 Cygni into one of the best-studied black hole binaries in the galaxy. Its behavior provides a reference point for comparing other systems with similar characteristics. The repeated outbursts have allowed scientists to test models of accretion and feedback under different conditions, building a more comprehensive picture of how such systems evolve over time. The continued monitoring of V404 Cygni also demonstrates the importance of international collaboration in modern astronomy. Each observation adds to a growing archive that not only documents the activity of this single system, but also informs broader theories about the behavior of black holes throughout the universe. The historical progression from an unidentified variable star to one of the most studied black holes illustrates the transformation of astronomical science itself. Where once humanity relied on photographic plates and optical telescopes alone, we now observe the universe through a spectrum that spans from radio waves to gamma rays. The discovery and ongoing study of V404 Cygni represent a triumph of both technology and persistence, showing how long-term observation can reveal the hidden nature of even the most enigmatic cosmic objects. Every new outburst provides another opportunity to refine our understanding of the universe's most powerful forces and to witness firsthand the dynamic and ever-changing nature of the cosmos. Modern observations of V404 Cygni have been transformed by the technological revolution in astronomy, allowing scientists to monitor and analyze its behavior in far greater detail than ever before. Observations from both ground-based and space-based telescopes now provide continuous data across multiple wavelengths, enabling a comprehensive view of the black hole's complex activity. The use of advanced instruments such as NASA's Chandra X-ray Observatory, ESA's XMM Newton, and the SWIFT satellite has made it possible to detect and interpret fluctuations in brightness that occur on scales of seconds to minutes. These fluctuations offer crucial clues about the structure and motion of matter within the accretion disk and the magnetic environment surrounding the black hole. In parallel, radio observatories such as the Very Large Array and the Meerkat network have traced the jets expelled from the system, showing how streams of energetic particles emerge and evolve over time. Together, these facilities have transformed V404 Cygni into one of the most thoroughly monitored black holes in the Milky Way, turning it into a cornerstone for research into high-energy astrophysics. The integration of the multiple observational platforms has been essential for uncovering the fine details of the system's dynamics. the swift satellite designed for rapid response to X-ray and gamma-ray events, has repeatedly captured V404 Cygni's sudden flares, allowing immediate coordination with optical and radio telescopes on Earth. The Chandra Observatory, with its high-resolution X-ray imaging, provides precise measurements of the radiation emitted by the accretion disk, enabling researchers to model the geometry of the region surrounding the black hole. Meanwhile, the Very Long Baseline Array combines data from antennas spread across continents to create images of the jets with extraordinary spatial resolution. These collaborations across instruments and continents have made it possible to track the evolution of individual flares from their origin near the event horizon to their appearance in the distant radio jets, effectively following the life cycle of energy as it moves through the system. Beyond electromagnetic radiation, advances in other forms of astronomical detection have opened new ways to study systems like V404 Cygni. Instruments sensitive to gravitational waves and neutrinos are expanding the frontiers of observation. Although no gravitational waves have yet been detected from this particular system, theoretical models predict that close binary systems involving black holes should produce such signals as their orbits evolve. Detecting these ripples in spacetime from a stellar mass system would provide direct confirmation of general relativity under conditions of intense gravity. Similarly, neutrino observatories such as IceCube have begun searching for high-energy neutrinos that might be produced in the jets of active black holes. These elusive particles, which travel vast distances without interaction, could carry information about the most extreme processes near the black hole, complementing the data gathered from electromagnetic observations. Modern technology also enables continuous monitoring of V404 Cygni's variability over long timescales. Automated sky surveys such as the Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory systematically scan the sky for changes in brightness, ensuring that no new outburst goes unnoticed. When the system brightens, suddenly alerts are sent across a global network of observatories, triggering rapid follow-up observations in multiple wavelengths. This system of coordinated response has transformed time-domain astronomy into a field that operates almost in real time. Astronomers can now watch as a black hole system evolves hour by hour, capturing events that were once lost due to limited observation windows. Advances in computational modeling are equally vital to understanding the immense volume of data gathered from these observations. Supercomputers allow scientists to simulate the behavior of accretion disks, magnetic fields, and relativistic jets under conditions that closely mimic those observed in V404 Cygni. These simulations incorporate equations from general relativity and magnetohydrodynamics, reproducing how matter flows around the black hole and how energy is released. The ability to compare simulation results directly with observational data provides a powerful tool for testing theories about how black holes operate. For example, models now suggest that the observed variability in X-ray emissions can be explained by magnetic reconnection. Events, moments when magnetic field lines within the accretion disk snap and rejoin, releasing vast amounts of energy. Such simulations have helped bridge the gap between theoretical physics and the observed behavior of real systems. Modern spectroscopy has further refined our understanding of the system. By examining the spectra of the radiation emitted from V404, Cygni scientists can measure the temperature, velocity, and chemical composition of the material in the accretion disk. Doppler shifts in these spectra reveal how fast the gas is moving, with some regions orbiting the black hole at a significant fraction of the speed of light. The chemical signatures also indicate that the companion star's material has been altered by the intense environment, showing evidence of nuclear processing. These measurements allow astronomers to determine how much material is being accreted and how efficiently the black hole converts matter into energy. They also help refine estimates of the black hole's spin, a critical parameter that influences how it interacts with its surroundings and how much energy it can extract from infalling material. The combination of modern observation and data processing has made V404 Cygni a laboratory for studying relativistic effects. The timing of the X-ray pulses reveals how gravity warps time near the event horizon, while polarization studies show how light is bent and twisted by the curved space-time around the black hole. These measurements confirm many predictions of Einstein's theory of general relativity and offer a direct look into the behavior of light under conditions of extreme gravity. By analyzing the delays between the emission of different wavelengths, scientists can reconstruct the structure of the region immediately surrounding the black hole, mapping how the disk corona and jets are connected. The rapid progress in observational capabilities has also deepened the collaboration between professional and amateur astronomers. Because V404 Cygni can become visible in optical wavelengths, during major outbursts, skilled amateur observers using small telescopes can contribute valuable data on brightness changes. These observations, when combined with data from professional observatories, extend the temporal coverage of events and help confirm short-term variability patterns. This collaborative approach embodies the evolving nature of modern astronomy, where large-scale facilities and individual observers work together to capture fleeting cosmic phenomena. Looking ahead, new generations of instruments promise to reveal even more about systems like V404 Cygni. The James Webb Space Telescope, though primarily designed for infrared observations, has the sensitivity to detect faint emissions from the heated dust surrounding the system. Upcoming X-ray missions such as Athena and Lynx will provide higher resolution and broader energy coverage, offering an even clearer view of the processes near the event horizon. Meanwhile, improvements in radio interferometry will allow scientists to observe the jets with finer precision, tracing their structure and evolution on scales never before possible. Each technological advancement brings us closer to a complete understanding of how black holes behave and how their energy influences the universe around them. The study of V404 Cygni demonstrates that progress in science often depends as much on technological innovation as on theoretical insight. The combination of advanced instrumentation, computational modeling, and global cooperation has transformed what was once a mysterious flickering light in the sky into one of the most detailed case studies of a black hole system. Through constant observation and analysis, astronomers continue to refine their understanding of how matter, energy, and gravity interact under the most extreme conditions known to nature. In doing so, they not only uncover the secrets of V404 Cygni, but also expand humanity's broader knowledge of the cosmic processes that shape galaxies and ultimately the universe itself. Theoretical models and simulations have become essential tools for explaining the complex behavior of V404 Cygni and systems like it. Observations alone, while detailed, can capture only a fraction of the processes that unfold near a black hole. To understand what drives its unpredictable bursts, immense luminosity, and the structure of its accretion disk, scientists rely on physics-based models that recreate the extreme conditions surrounding the event horizon. These simulations are built on the equations of general relativity and magnetohydrodynamics, which describe how gravity, matter, and magnetic fields interact in curved space-time. By combining these equations with observed data from telescopes, researchers can create three-dimensional representations of how matter spirals into the black hole, heats up, and releases energy before crossing the event horizon. The results of these simulations reveal the astonishing complexity of the environment near V404 Cygni, and show how tiny variations in the flow of material can lead to dramatic outbursts detectable across the galaxy. One of the central challenges in modeling such systems is understanding the role of magnetic fields. Simulations show that as material from the companion star falls into the accretion disk, magnetic field lines become twisted and stretched by the disk's rotation. Eventually, the tension in these fields causes them to reconnect, releasing immense bursts of energy. This process, known as magnetic reconnection, is thought to be one of the primary mechanisms behind the sudden X-ray flares observed in systems like V404 Cygni. Reconnection events can occur repeatedly, generating cycles of high and low luminosity that match the variability seen in real data. By adjusting the strength and configuration of these magnetic fields in their models, scientists can reproduce many of the observed features of V404 Cygni's emissions, including the rapid fluctuations and episodic outbursts that define its behavior. These models also suggest that the jets emitted from the black hole's poles are directly tied to the structure of the magnetic field, with the energy released by reconnection events helping to launch and sustain them. Another key aspect of theoretical work on V404 Cygni concerns the dynamics of its accretion disk. High-resolution simulations reveal that the disk is not a flat uniform structure, but a turbulent and layered environment. The outer regions are cooler and thicker, while the inner regions near the black hole are thinner and hotter. Instabilities within these layers can cause portions of the disk to collapse or expand, suddenly altering the flow of material and the amount of energy released. These structural changes correspond closely to the observed light curves of V404 Cygni, where brightness rises and falls unpredictably. In some simulations, shock waves ripple through the disk as denser clumps of gas spiral inward, temporarily increasing the X-ray output before the system settles again. This dynamic process illustrates how the delicate balance between gravity pressure and magnetism determines the observable behavior of black holes. Theoretical studies also address one of the most elusive aspects of black holes: their spin. The rotation of a black hole affects nearly every feature of its environment, from the shape of the accretion disk to the power of its jets. Models suggest that V404 Cygni's black hole spins rapidly, possibly near the theoretical maximum allowed by general relativity. A fast spin means that the black hole drags space-time around, with it a phenomenon known as frame dragging. This twisting of space-time alters how material orbits the black hole, and may enhance the efficiency with which energy is extracted from the accretion disk. In rapidly spinning systems, magnetic fields anchored in the disk can tap into the rotational energy of the black hole itself, powering the relativistic jets that shoot into space. Theories such as the Blandford-Znajek mechanism describe how this process works, and are now supported by observations showing a strong correlation between spin rate and jet power in systems like V404 Cygni. Numerical simulations have also helped scientists explore how radiation behaves near the event horizon. Light emitted from the inner regions of the accretion disk is bent and distorted by the black hole's gravity before escaping into space. This gravitational lensing effect can cause the disk to appear warped or brighter on one side when viewed from certain angles. Simulations of this light distortion match the patterns observed in real X-ray spectra and polarization measurements. The polarization of light, its orientation as it travels, reveals information about the magnetic fields and geometry of the emitting region. Theoretical models have successfully replicated these observations, confirming that the strong gravity and curved space-time near V404 Cygni's black hole significantly affect the light that reaches us. In addition to explaining the behavior of V404 Cygni itself, these models provide a framework for understanding other similar systems across the universe. By varying parameters such as black hole mass spin and the rate of accretion, scientists can simulate a wide range of conditions from small stellar mass black holes to the supermassive ones at galactic centers. The physics remains fundamentally the same, differing only in scale. This universality allows the lessons learned from V404 Cygni to be applied broadly, linking the study of individual black holes to the evolution of galaxies. Simulations show that the feedback processes seen in V404, Cygni energy outflows, radiation heating, and matter redistribution also occur on far larger scales in galactic nuclei shaping star formation and the growth of galaxies over cosmic time. The complexity of these theoretical models demands enormous computational power. Supercomputers running for weeks can simulate only a few seconds of real time near a black hole. Yet the insights gained from these efforts are invaluable. They allow scientists to test ideas that cannot be verified through observation alone. For instance, simulations help explore what happens inside the event horizon, even though this region is forever hidden from view. While no information can escape from beyond this boundary, modeling how matter behaves as it approaches the horizon provides indirect clues about the conditions inside. These studies probe the limits of physics, where general relativity and quantum mechanics intersect, hinting at the need for a more complete theory of gravity that can unify these two frameworks. Collaboration between theorists and observers has become central to modern black hole research. Observational data from V404 Cygni feed directly into simulations, while theoretical predictions guide where and when to look for specific signatures. This feedback loop allows models to evolve rapidly as new information becomes available. Each new observation, whether a burst of X-rays, a change in radio brightness, or a shift in spectral lines, offers a test for existing theories. When discrepancies arise, models are refined, leading to a more accurate and comprehensive understanding of the system. In this way, V404 Cygni has become both a testing ground and a benchmark for the study of accretion magnetism and relativistic physics. As computing power continues to grow and observational technology advances, the gap between theory and observation will narrow even further. Future simulations will incorporate more precise physics, including the effects of radiation pressure, magnetic turbulence, and relativistic particle acceleration. These models may one day reproduce the behavior of V404 Cygni in real time, offering an almost cinematic view of matter spiraling into the black hole and jets erupting into space. The study of this system demonstrates the power of combining human imagination, mathematical theory, and technological progress to illuminate the most extreme environments in the universe. In bridging the unseen with the observable, theory transforms abstract equations into vivid dynamic portraits of a cosmos governed by gravity and light. The future of V404 Cygni, like that of many binary systems containing black holes, is shaped by the slow but relentless exchange of matter between its two components. Over time, the companion star continues to lose material through the gravitational pull of the black hole, transferring mass and energy that fuel the system's immense luminosity. This gradual process has been ongoing for millions of years, and will eventually lead to the complete transformation of both objects. The companion star, steadily stripped of its outer layers, will grow smaller and cooler until it becomes a remnant of its former self. As its mass decreases the rate at which it feeds, the black hole will also decline, leading to a gradual reduction in activity. The bright X-ray outbursts that have defined V404 Cygni's history will become less frequent and less powerful, eventually giving way to long periods of quiet. The black hole will persist, of course, but its feeding cycle will slow until only faint occasional emissions remain, marking the system's eventual transition into a dormant state. The long-term evolution of V404 Cygni is governed by the interplay of gravitational and magnetic forces. The orbital path between the black hole and its companion is likely to change as mass transfer continues. Currently, the pair completes an orbit roughly every 6.5 days, but this period will lengthen as the star loses material. The gravitational interaction that drives the mass transfer may weaken, reducing the rate at which gas is drawn into the accretion disk. The magnetic fields that shape the system's energetic jets will also evolve, changing in intensity as the accretion process diminishes. Over vast spans of time, these changes could lead to the complete cessation of jet activity, leaving behind a silent black hole surrounded by the remnants of a once turbulent disk. While the timeline for these transformations extends over millions or even billions of years, the data collected from V404 Cygni today offers insight into how similar systems age. Observing how the black hole's emissions fade and how its companion star evolves provides astronomers with a model for predicting the future of other binary systems. Eventually, the companion star may exhaust its fuel entirely and collapse into a dense remnant, possibly a white dwarf. At that point, the mass transfer process would all but end. The accretion disk, deprived of a steady supply of material, would cool and dissipate, leaving behind a faint shell of gas and dust. The black hole would remain invisible unless it encountered new material to accrete. In this dormant phase, it would drift through the galaxy as a dark, silent object detectable only through its gravitational influence on nearby stars. The current activity of V404 Cygni suggests that it still has a significant amount of life left in its active phase. The companion star, though smaller than the Sun, still contains enough mass to sustain the accretion process for millions of years. Each new outburst observed in the system provides data that helps refine estimates of how long this active period might last. By studying the rate of mass transfer, scientists can model the eventual decline in activity and predict when the system might begin its transition to dormancy. These predictions, while uncertain, suggest that the black hole will continue to experience occasional outbursts long after current generations of astronomers are gone. The study of V404 Cygni's future is not only about understanding one system's fate, but also about exploring the broader life cycles of black holes and their companions. Many similar systems exist throughout the galaxy, each at a different stage of evolution. Some are newly formed from the collapse of massive stars, while others are nearing the end of their active lifetimes. Comparing these systems allows scientists to reconstruct the full timeline of binary evolution from formation to quiescence. V404 Cygni serves as a particularly valuable case because it sits at a middle stage, neither newly formed nor nearing extinction. Its current behavior offers a snapshot of the phase during which black holes are most active, feeding vigorously and producing dramatic bursts of radiation. The long-term fate of such systems also has implications for the distribution of black holes across the galaxy. As binary systems evolve and their companions are consumed, the resulting isolated black holes contribute to a growing population of dark solitary objects. These dormant black holes are invisible to most forms of observation, detectable only through their gravitational effects. Astronomers estimate that hundreds of millions of such black holes may exist in the Milky Way, drifting unnoticed through the galactic disk. The remnants of systems like V404 Cygni will eventually join this hidden population, continuing to shape the galaxy's structure through gravity, even after their luminous phases have ended. Predicting the precise future of V404 Cygni also involves understanding the long-term stability of its orbit. The gravitational radiation emitted by close binary systems causes their orbits to shrink gradually, though the effect is small. Over extremely long timescales, this loss of orbital energy could bring the two bodies closer together. If the companion star remains massive enough, the system might eventually undergo a catastrophic merger, releasing an enormous burst of energy. Such events are rare but have been observed in other systems where the final stages of mass transfer end in a sudden and violent collapse. However, for V404 Cygni, the most likely outcome is a slow and steady decay of activity rather than an explosive finale. As time progresses and the system's energy output fades, it will become increasingly difficult to detect. The jets that once blazed across space will dissipate. The X-ray emissions will weaken, and the system will settle into a faint glow, visible only in the infrared spectrum. The black hole will remain as a silent testament to its past activity, a remnant of a once luminous partnership that profoundly influenced its surroundings. In this way, V404 Cygni's eventual quiet phase mirrors the larger cycle of cosmic evolution. Stars are born, shine brightly and fade, while black holes feed, flare and grow dormant. The eventual dormancy of V404 Cygni will not mark an end to its scientific significance. Even as its emissions fade, the data gathered over decades will continue to inform future research. The system has already provided a blueprint for understanding how matter behaves in extreme gravitational fields, how magnetic fields generate jets, and how accretion drives radiation across the universe. Its long record of activity ensures that even after its light fades, its legacy in the study of astrophysics will endure. Through V404 Cygni, humanity has gained a window into the life and evolution of black holes, from their violent outbursts to their slow descent into silence, a journey that reflects both the dynamism and the eventual stillness that characterize the universe itself. The mystery of active black holes like V404 Cygni continues to challenge and expand human understanding of the universe. Even with decades of observation, detailed modeling and theoretical exploration, questions remain about the processes that drive their immense power and unpredictable behavior. These cosmic engines of gravity and light represent one of nature's most extreme manifestations of physics, a point where matter, energy and space converge in forms that defy everyday intuition. Despite the enormous progress made in observing and simulating such systems, the precise mechanisms behind their fluctuations, jet formations, and transitions between quiet and eruptive states are still not fully resolved. Each new observation brings a step closer to comprehension, while simultaneously exposing new layers of complexity that remind scientists how much remains unknown. V404 Cygni stands as an emblem of this balance between knowledge and mystery. It is both one of the most thoroughly studied black holes in the Milky Way and one that continues to surprise researchers with its erratic bursts and unique structure. The system's intense X-ray outbursts, alternating with long intervals of silence, illustrate how fragile the equilibrium within an accretion disk can be. It is not a steady process of consumption, but a turbulent dance of attraction and release, guided by forces that are still being mapped and quantified. The interplay of gravity, magnetism, and relativistic motion within such a compact region of space remains difficult to replicate precisely in simulations. Yet every pattern of light and shadow captured by telescopes offers a coded message from the frontier of physics, a glimpse into the behavior of matter at the very limits of what natural laws allow. The continuing study of this system also deepens the broader understanding of how black holes influence the universe on every scale. The same principles observed in a stellar mass black hole like V404 Cygni can be extended to the supermassive black holes that anchor galaxies. The way accretion disks form heat and emit radiation follows the same physical rules regardless of size. This universality allows astronomers to treat systems like V404 Cygni as smaller, faster laboratories for processes that unfold over millennia in the centers of galaxies. What happens here in hours or days may take millions of years elsewhere. The insights gained therefore provide not only an understanding of one object, but also a bridge toward comprehending the evolution of the cosmos itself. Yet even with this knowledge, many questions remain stubbornly unanswered. Scientists do not yet fully understand why some accretion disks become unstable, while others remain steady for long periods. The exact mechanism by which magnetic fields generate and sustain relativistic jets is still debated. Observations have confirmed the presence of immense magnetic structures near black holes, but how they store and release energy remains elusive. Similarly, while theories like the Blandford-Znajek process describe how rotating black holes might power jets, the efficiency and variability of this process differ from one system to another. V404 Cygni's jets, for instance, appear and vanish in rapid succession, suggesting an additional layer of physics not yet captured in existing models. The radiation emitted from the black hole's surroundings also raises puzzles. Some emissions are consistent with predictions of thermal radiation from the hot accretion disk, while others show non-thermal characteristics that imply the involvement of particles accelerated to near-light speeds. Understanding the exact contributions of these processes requires both more sensitive instruments and refined theoretical frameworks. Future telescopes will likely be equipped to detect even smaller variations in timing and energy, offering a more detailed look into how these emissions originate. Instruments capable of capturing polarized light at multiple wavelengths could reveal the orientation of magnetic fields around the black hole, providing direct evidence for the structures long hypothesized by theory. Another enduring mystery lies in the behavior of time and space near the event horizon. The predictions of general relativity describe how time slows and space curves under extreme gravity. Yet these predictions have never been tested directly around a stellar mass black hole with the precision achieved for supermassive ones. V404 Cygni provides an opportunity to explore how these relativistic effects manifest on smaller scales. By comparing the timing of its X-ray flares with the motion of the accretion disk, scientists can probe how gravity distorts light and time in its immediate vicinity. These measurements may one day help reconcile general relativity with quantum mechanics, a goal that remains one of the greatest challenges in modern physics. Despite the complexity of these challenges, the fascination with black holes like V404 Cygni lies in their ability to reveal fundamental truths about the universe. They transform invisible gravity into visible light, converting the collapse of matter into radiant energy that can be detected across thousands of light years. They demonstrate the unity of nature's laws, where the same forces shaping atomic particles also sculpt galaxies. Every discovery made about systems like this extends beyond a single object, touching on questions of origin, structure, and destiny that lie at the heart of cosmology. As observational technologies evolve, the next generation of instruments will continue to peel away layers of uncertainty. New X-ray and radio observatories will map the behavior of accretion disks with greater accuracy, while gravitational wave detectors may one day capture the subtle tremors produced by orbital changes in the system. Each advancement brings the possibility of transforming long-held theoretical assumptions into observable reality. The work of countless scientists, astronomers, physicists, engineers, and data analysts converges in this pursuit, reflecting the collaborative nature of discovery that defines modern astrophysics. V404 Cygni's continuing study is therefore more than an effort to understand a single black hole. It is part of humanity's broader endeavour to comprehend how the universe functions on its most fundamental levels. The system's bursts of light and energy are more than cosmic spectacles. They are signals from the frontier of knowledge, revealing both how much has been learned and how much remains to be uncovered. Though the object itself will one day fade into quiet isolation, its legacy in science will persist. The data gathered across decades will remain a foundation for future generations to build upon, long after its last flare has dimmed. The mystery of V404 Cygni is not merely in its violent outbursts or its immense gravitational pull, but in what it symbolizes: the balance between understanding and wonder. Every observation brings clarity, yet each answer reveals new layers of questions that pull inquiry ever deeper, much like the gravity that defines the black hole itself. In its cycles of eruption and stillness, brilliance and shadow, it mirrors the rhythm of cosmic exploration, an endless process of discovery that continues to draw humanity toward the luminous heart of the unknown.